figure 1914. So, this schematic is the least done in today's world. In fact, it really isn't done much at all anymore. This was the standard up until around mid-1990s. So you will see it on a bunch of old drawings. You have the simplified, which is now the ANSI standard up to 1 inch diameter. Once you get larger than 1 inch, you go to the detail representation, which is the closest approximate of how the thread looks. Okay, so know those three, and when to use them. We had a bunch of definitions that went right at the start. Okay, so you should know these major ones here. And what I'm going to focus on are the ones we need to draw. What do we need to draw? We need major diameter. We need the minor diameter. We need pitch. We need TPI. And I think that's all we really need for representing our threads. Well, if we're doing detailed representation, we need our included angle. Now, while we're on these definitions, there's one other thing that you also need. And let me see if you folks can come up with the correct term. This will be a Jeopardy section. The distance a thread turns in one 360-degree rotation. Alex, what is a? Let me give you a hint. I got a leash. I clip it onto my dog's collar, and I
Run. No. I know, we should know
yes,
this. We just did.
yes, I walk them, but I
Lead.
Yeah,
It's the lead right here.
lead. I lead them.
19.4.
Figure 19.4.
Yeah.
Couple pages past where I'm at.
Well, yes, we need it. Single.
And that has to deal with the slope of this, right? Okay. So no lead. We also talked a little bit about thread form right over here. And I just kind of hit some of the biggies. I'm going to come back and kind of hit these more later. But for now, keep in mind what we've got a bunch of 60-degree teeth here. We've got the Unified National and Unified, which are our ANSI standards. We've got our metric, which is the ISO standard. And then we talked about some of the others, the American Nationals based off the old Sellers thread. We've got the 55-degree Whitworth down here. I don't think I've really mentioned too much about the knuckle, but I should. I think the video hit this one. The knuckle thread is a sheet metal screw. It's a self-cutting thread.
That's cutting and it's round.
Mm-hmm. Yep. This is greatly exaggerated. Okay. If you look at a sheet metal screw, it's very, very small round.
Yeah, but I would have said that, like,
Yeah. And
the other ones are.
threads we're going to go into very quickly are like the buttress and the acme, which are power threads. But you should be somewhat aware that the form and what it's used for. For the most part, what we're looking at here is you got your Whitworth, metric, unified. These are fastening and adjusting applications, not power applications.
And the Whitworth, you just know that it's an older type.
Yeah, it's an older thread.
That was replaced with the Unified.
Yeah, it actually started with the Whitworth, and then it went to the American National, which is still a pretty popular thread. I call it the seller's thread. He's the guy that came in and changed that. But Whitworth made the first standard thread that was cut on a machine that we started using in industry. And then Sellers adapted it, and then it's been adapted again for the Unified. And that was back in the 40s, and it hasn't really changed since. What do we use threads for? 3 things.
Adjusting,
Adjusting the position,
tightening,
clamping,
Clamping.
fastening, let's just say temporarily fastening, and,
Power transmission.
yeah, these ones down here, power. Augers, gears, those are all threads. Anybody seen a square thread? I've only seen one, and it was a pretty cool situation. I just went, so I was over in Bavaria, and I was taking this train, and the train was going up the Alps, and it got onto like this 70-degree incline, and of course the train can't go on that because it'll slip. They actually had cog wheels on it that were square, and they fit in pegs, and the thing just walked right up the side of it. You were sitting there back there, kind of like this, almost at an amusement park, and heading up into the Alps. It was pretty darn cool. I think a lot of your what do we got now at amusement parks that use the same thing? Everybody goes loop to loop.
oh yeah.
Use that.
Yeah, a lot of them, that's how they climb. They use pulleys now and stuff, but the old days, that's what they had, was the old square cog wheels.
Was that the thing where you were kind of jerking as you went up?
Uh-huh. It jerks on every one. What else do we have on here? Oh, we got a couple other important items. Page 913. If we're drafters, we ought to understand this. A thread note. I will test over this thread note. Know the components of it. Any questions on that thread note? So the English version, 913. The metric version, I'm only going to go this deep on page 917, which is diameter and pitch. What does the M signify?
Metric.
Yep. And that is part of your note.
We're supposed to put the diameter symbol
Yep.
before the end.
Yep. Diameter goes right before it. It is tempting to come in and take a thread, since we see a really good look at it right here. Remember, positive cylinders are dimensioned in the rectangular view, but since threads are a specialty type of negative or positive cylinder, we use leader lines. Okay. You can include counterboring, capping, all that information with it. I think the rest of the chapter is mostly about drawing. One more question I've got for you folks. What's the difference between a temporary fastener and a permanent fastener? If you have to destroy the fastening method, it's a permanent fastener. If you don't destroy the fastener, it's a temporary fastener. So we've got nuts, bolts, clips, pins, all these things are temporary fasteners. Permanent fasteners are glue, welding, friction fits, all of these types of things. Or to get them apart, I have to destroy the fastener. rivets are a permanent fastener. Any questions on chapter 19 that I didn't cover? Okay, the last thing we did was 18, GDT. Geometric dimensioning and tolerancing. Controlling variations in the geometric form. That's really what you're doing here. Controlling variations in the geometric form. It is really meant to make parts more accurate yet cheaper. By that statement, I'm just going to look at one right here. Now, for me to take and make sure this is a concentric deal, that these are concentric, I would have to use tolerancing on all of these dimensions to a high degree. Therefore, the entire part, since I'm going to very strict tolerances, gets very expensive. Because I need machinery to do that, I need a very technical workforce to do that. So in essence, what I can do is say, you know, what's really only important here is that these are concentric so that they mate correctly. So let's just spend the money on that, and let's drop our tolerances on this stuff so they're cheaper. In essence, we can then provide a high degree of precision on the concentricity of these two, and then the size of them doesn't really matter, or doesn't matter as much. Okay? So we can reduce the cost. That's ultimately what we are trying to achieve here. What's the general rule if no GDT is listed in a drawing? If you do not use GDT on a drawing, then what does GDT default to? It defaults to all the main tolerances. To use GDT, I'm going to go to the correct page here. Page 877. So when we apply GDT, we use a feature control box right here. It has some components on it. The first part of it is the geometric symbol, whether we are using diameter, position, parallel, flatness, straightness, run out, angularity, perpendicular, these types of symbols. So what is the form we're trying to control? That's the first thing. Second thing that goes in there is the tolerance. Now this is a separate tolerance from the tolerance on the drawing now, right? So we're coming into just the form. Then we follow that by a condition when the tolerance takes effect. Remember that? Circle L, circle M, circle S. You see them right here, these two and that one. Those are the three we covered because they're the majority of them. Maximum material condition, least material condition, or regardless of feature size. After that, we then come into how we are going to measure it, or what it's related to. Keep in mind, not all geometric forms are related to some other form. But when we do, we call them a datum. A datum is a theoretical perfect plane or point used as a reference. Yes.
Item 30, do you have to specify FL or S?
No.
You don't have to.
No, if you don't specify a condition, so then it's going to default to regardless of feature size.
Well, okay, but you don't have to put that on there.
Well, you should put it on there.
So like in our drawings, we should put that on that one that we did? Yes.
Yeah, I would. I mean, but this basically is what everybody defaults to if it's not included. We kind of went over that example. Remember going over that where we explained how those conditions work? I can throw my notes back up here. I wrote all that out. Okay, so here was our two conditions. Let's just kind of review on how this works. Okay, so here we looked at straightness, and here is circle S for regardless of feature size. Now, if you don't put anything, they're probably defaulting to this, but it's an incomplete box if you don't put it. Okay? Being as how we are pretty picky about our stuff, let's make sure it's there. So what this means is, it's got a tolerance of 0.02 regardless of feature size. So the first thing that's checked is, this thing is checked is at 1.01 to 0.99. If it's not, this part's rejected right off the top. Okay, it's gone. But if it is in 1.01 to 0.99, you all see where I get those numbers, right? If it's in that zone, then we apply another tolerance of 0.02 to it, so that it's not a big banana or something like this and it won't fit into a hole. Okay. So if it comes off at 1.01, that's an acceptable size. Well, it can really now, at that location that we can do, it can be 1.01 plus or minus 0.02. If it comes off at 1, okay, and that's the size that we measure the cylinder at, then we apply that tolerance also.
Does that go in its own box though, the S, like when you have, so?
No, it goes right after the tolerance.
But it doesn't, you don't draw a line in
No,
the
no.
box?
Nope.
So, are you paying attention to it more when you're doing quality control? Or
This is all done during quality control.
none of this is done during the building process?
No, they're doing it during the building process, but they're using gauges and they've got their machinery set up. And a lot of it might be automated. You know, it's tough to say for the individual circumstance on how it's actually done.
So if you were given this and you were going to build it, how would you approach it to know where to go with it?
You'd probably build yourself a test right there on the thing. And so you build it and you can just run it through a hole or something and say, oh, you know, this isn't fitting. So quality control is going to throw it back. Yeah, that's what they'll end up. And so what we're doing, like on this with the cylinder, we're trying to make sure this, let's just set up the scenario. So here I have a hole going through a part, and this hole is at its smallest size, 1.03. Okay. Now I'm going to take this shaft, and that thing's a cylinder, but let's say I build the thing and it looks like this. Now I can come along here and I can measure it right here, and I can measure it right here, here, and here, and let's say I get 1.00 on all those measurements. So it passes, right? Because that's a size deal right here. Then I'm going to take a look at this center line of this thing. Okay. And I'm going to just pick a spot, and everywhere I measure on that center line now has to be within plus or minus 0.02 of that size. That will ensure, because it can come off at 1.01 plus 0.02 is 1.03, I can get that in that hole. Right? I can get this at 1.04 in here. Yes,
So-
Juan.
So those on the right are the variations of,
Mhm. Yep,
So you gotta make sure you have a leader line going to the center line, not just the
That's correct.
object itself, so they know exactly where you're.
yeah. You could also point this to an edge, and then they would measure the edge. In this case, I pointed to the center line.
But either one would be okay with that.
Probably.
So you're saying, by the upper one, you're saying that that's, this, and that's this part.
That's the
And
size.
The second one is where you're checking the overall, the lower diagram,
Yeah.
where that kicks in.
Right, because I've got to get that in, and if I've got this type of shape, where let's say I from here down, I've got 0.05 off. Well, the thing passes on sides, right? But then I try and stick it in the hole, what's it gonna do? It's gonna bind. Right there, right? And I can't go any further with it. We're talking about metal, you know, something that is much stronger than we are. You kind of get it? Then we go to maximum material condition. Okay. Now on this one, we can actually get sloppier the further we get away from it. Because it's set up to work at the closest allowance or fit. So that's kind of a review of what those material conditions do for you. Okay. Now keep in mind, this is very detailed. I don't know as a drafter if you're really going to be doing this stuff on your own until you get some experience. Okay. And then you're going to be dealing with it with the production crews, because you may give them a tolerance that they can't build on that floor. Okay. And that's not something that's really acceptable. Management would need to know, hey, we gotta buy some machines, or we gotta do something different here for us to accurately build these parts. And it can get very expensive, and then an analysis made, say, oh, it's not worth it. We're not gonna make that much money on this project. Like Jim across the hallway just bought a new lathe, $180,000 for one lathe. Okay, so obviously we've got to make a bunch of parts and make a bunch of money to pay for that lathe and the person running it. Okay, but the lathe he's got will do this stuff very easily. His old lathe would, he couldn't even build a screw thread on his old lathe. So be that as it may, this is really what that condition gives you. Does everybody understand the difference between a related and an individual GDT? Okay, in essence what you want to do, when we're talking about related versus individual, when you're looking at a symbol, is it related to itself or is it related to another part? So, to itself or to another part. So the easy ones to pick on here are parallelism. If I've got an object that has to be parallel to something, it's got to be related to another object, right? Because I've got to have two things that are parallel. It takes two items. So that is what we would call a related GDT. Perpendicular, where you're coming like this. Again, two items that are related. Concentricity, two cylinders that are related. You must have datums with related GDTs because you got to tell them what you're going to measure against. You have some that are not related. They are what we call individual, like flatness. Flatness is an individual GDT. I've got a tabletop. I'm comparing the tabletop flatness to itself.
What about slope?
Slope is a single line. Okay, it is an individual. Straightness is an individual.
Slope's not in relation to anything else.
No.
Okay.
Runout is individual.
what
Yes.
about the one with the angle?
singularity is a related. Okay, because you're gonna have two lines that you have to measure the angle on. Okay, and that's always what you ask yourself, and that will kind of pop it out. Am I having to measure off of this object for something else to get my solution? Sean, does that kind of help a little?
Yes, thank you.
Yes, Cheryl.
When we went over this originally, you said, you pointed out the ones that were important.
Mhm.
Is that what we need to know for the test, or do we need to know everything?
If I do any of this, I'll give you a chart that's got everything on it. But I can tell you right now, I asked mostly theoretical questions. I left most of this tolerancing. I'm going to ask just as many questions on tolerancing, the end of chapter 17 as a review, versus GDT. I think I've got 7, 8 questions on the test for that section. And I guess I should have mentioned that earlier, but we did do a review on tolerancing chapter 17, remember that? Where we talked about what a unilateral tolerance is, what a bilateral tolerance is, what direct limits is. The concept of tolerancing the amount of slop, right? Or the limit of variation from the basic size. So it might behoove you, besides knowing what we just talked about, reviewing for yourself I'll give you the page here. Tolerancing starts on page 859. No, it starts sooner than that. Starts on page 843.